In this video, we'll take a look at some basic theorems about automorphism groups. First off, we see that for every graph G, the automorphism group of the graph is isomorphic, that's a group isomorphism, to the automorphism group of the complement of the graph. So really we can prove this, and it doesn't even require a proof, this is more of an observation, and we can see this by just noting that any automorphism of G preserves edges and non-edges, right? It preserves adjacency and non-adjacency. So what exactly, so it preserves both edges and non-edges. And then note that in the complement of G, edges are swapped with non-edges. So if an automorphism, if you have an automorphism of G that preserves edges and preserves non-edges, then it will also preserve edges and non-edges in the complement of the graph. So maybe just to illustrate this, we'll look at, how about P3? We'll look at P3 and its complement of P3, which would be isolated vertex together with a K2. So think about the automorphism group of P3. So we have the identity. We can swap. So let's say U, V, and W. So we have the identity, and then U has to remain fixed, right? U has degree 2. No other vertex has degree 2. So U has to remain fixed. And so the only other option here is swapping V and W. So V and W are swapped. So that means the automorphism group of P3 is just these two elements. And so this is isomorphic to integers modulo 2, as we've seen before. Now let's take a look at P3 complement. Well, we have this vertex, I'll call this U, V, and W. Well, because we're looking at the complement, I should label these the same way. So now U has degree 0 rather than degree 2, but it's still the only vertex of degree 0. And so it has to be sent to itself. So we have the identity automorphism, and then we can also swap V and W with each other. And so we get VW. So right, again, we get that the automorphism group of P3 complement now is isomorphic to the integers modulo 2. So in P3, right, we have this automorphism V and W. It preserved the edges UV, UW, and it preserved the non-edge VW. In the complement, VW preserves the non-edges UV and UW and preserves the edge VW, right? So edges are swapped with non-edges. However, the automorphisms preserve both edges and non-edges. So it also preserves edges and non-edges in the complement when those are swapped. And so in general, this is true that the automorphism group is isomorphic to the automorphism group of the complement of the graph. So this is a nice result. And now the next result, we're getting into what possible orders are there for the automorphism group. Remember, in group theory, an order of the group is the number of elements in the group. And for this, we need to use a group theory theorem, and that is Lagrange's theorem, which says the order of a subgroup divides the order of the group. So that is, if H is a subgroup of G, then the order of H, that this gives us an integer, and in particular, it's the index of H and G. Oh, did I write that backwards? I hope I didn't write that backwards. It's the index of H and G. I think I did. I think this should be H. G. Yeah, the index of H and G. It's the number of left cosets. We don't have to worry too much about this. The point is just what I've written here, is that the order of the subgroup divides the order of the group, that this gives us an integer. This is an integer. So this is a nice result, and now we'll couple this with a realization that if G is a graph, let's say if G is a graph that is not complete, i.e. there is some pair of adjacent vertices and some pair of non-adjacent vertices. So I should say not complete and not empty. So that is, we have, some pair of adjacent vertices and some pair of non-adjacent vertices. Well, then not every possible permutation is an automorphism. Then there is some permutation. There is some permutation of its vertex set that is not an automorphism. For example, you can't swap the pair of adjacent vertices with the pair of non-adjacent vertices. That would not preserve edges, right? That would not preserve edges, and so that permutation would not correspond to a automorphism of G. So what this means is that the automorphism of G, in this case, G is a graph with some pair of adjacent vertices, some pair of non-adjacent vertices, then automorphism of G is a subgroup of the automorphism group of Kn, which we know is Sn. So it is a subgroup of Sn, of all the permutations. Remember, Sn is the group of permutations of the vertex set of order n. So I should say here maybe a graph of order n. It's some subgroup of Sn. Pair this together with Lagrange's theorem. So we know that the order of Sn is n factorial. And so the automorphism of G, since it's a subgroup of Sn, it must divide n factorial. And so we get the following theorem. The order of the automorphism group of a graph of order n is a divisor of n factorial. And we can say even more, it equals n factorial if and only if G is not the complete graph or G is the empty graph. All right, so there's another nice fact. Let's move on to the final of these basic theorems. The number of distinct labelings of a graph G of order n from a given set n of labels is n factorial over the automorphism group of G, the order of the automorphism group. So, all right, so given a graph of order n, there are n factorial ways to, right, any permutation of the vertex set gives rise to a labeling of the graph, ways to label the graph using the same set of n labels. Right, we could use different labels and come up with, infinitely many ways to label it if we label it with, say, colors or, I don't know, other sets. So if we just fix the set of vertices, there's n factorial ways to label it because any permutation gives a labeling. However, some of these labelings are really going to be the same, right? These labelings are going to be the same if there's some automorphism to get from one labeling to the other. And so in particular, for a given labeling of G, each automorphism of G gives rise to an identical labeling of G. And so that is each automorphism, each labeling gives rise to automorphism of G, the order of automorphism of G, identical labelings of G. And so that means we have counted each labeling. So we have counted, if we count each of these n factorial labelings, we have counted each distinct labeling automorphism of G times. So maybe an example will help understand that. So here I'm going to use P3 again. So here's U, V, and W. I'll set up our adjacencies here. U adjacent to V, adjacent to W. So there's one labeling. So there are 6 labelings of this, right? Just sort of a priori, there are 6 labelings of this. I could also do U, W, V. I could also label it like, let's see, W, U, V. I could do W, V, U. Let me go one more down here. I could also do, let's see, let's put V up here. I could do V, U, W, or I could do V, W, U. And remember, we have the identity automorphism and we have the automorphism. So thinking of this one, we have the automorphism that swaps V and W. Actually, yeah, maybe I don't want to present it like that. Yeah, not quite. Anyway, so we have the automorphism that swaps these 2 vertices down here and keeps this one of degree 2 fixed. So the automorphism group here was Z2. The order of the automorphism group of G was equal to 2. And we'll notice that since we have this automorphism, so I have U, V, W, U, W, V, these are the same labeling, right? Because there exists an automorphism that swaps V and W. And so these 2 are really the same labeling. And there are exactly 2 of them, one for each automorphism, the identity and the swapping of these 2 vertices. Same thing over here, W's fixed, and then I have V and U. Well, here's the identity, and I also have this labeling where I swap these 2 vertices of degree 1. So I have 2 of those, and these again are the same labeling. Right? Remember, the same labeling means it gives rise to exactly the same edge set. And again, we have same labeling here. And so I have exactly 3 labelings, and so that was n factorial, here was 6. Divide that by the automorphism group of G, right? There were 2 of each kind of labeling. We double counted each labeling by listing all these out. We ended up with exactly 3 distinct labelings. So that's the idea, and in general, it is n factorial over the order of the automorphism group. And that's kind of neat. Okay, so next time we'll start talking about some more group theoretic stuff, orbits of vertices and similar vertices. I'll see you there.